Okay, let's take a look at chemical nomenclature, and you probably saw my announcement where I have a whole series of videos on my YouTube channel that cover this topic, and so we're going to go over it kind of quickly here, just using the slides that I have in the slide deck for our class. And so chemical nomenclature is nothing more than a system for naming molecules and ionic compounds as well. So just nomenclature generally is just a collection of rules for naming things. Compounds are identified both by their formula, but you also have to be able to communicate a name, right? We don't walk around saying Na2CO3. No, it's got a name. We call it sodium carbonate, right? We don't walk around just giving a formula for ammonium chromate. Okay, there's a formula for it, and so we're going to learn how to name the following types of inorganic compounds. We're going to name ionic compounds. We're going to name molecular binary compounds. So those are compounds that are only made out of two elements. Then we're going to look at ionic compounds that contain polyatomic ions. So you've got to commit the polyatomic ions to memory, like I said. And acids, so things like hydrochloric acid, sulfuric acid, hydrosulfuric acid, I guess, as well. Anyhow, so let's start with ionic compounds, okay? If you want to name an ionic compound, here's all you got to do. You got a metal and a non-metal. Well, the metal is the cation. And so you just name the cation, and I mean you just name it. So sodium, potassium, calcium, etc., etc. Okay, and then the anion that follows it. Okay, it says a monatomic anion is given the name of the element, and then you replace it with the suffix "ide." Okay, so you change the suffix to "ide." So here instead of chlorine, it would be chloride. Here instead of bromine, it would be bromide. Here instead of oxygen, it would be oxide. Here it would be sulfide. Come on. Sulfide, nitride, etc., etc. So let's see if we can name some of these. You have to bear with my handwriting a little bit. But the first one is going to be sodium. We just name the cation, and then we have not chlorine, chloride, okay? Next one, we have potassium. So potassium. And we have bromine, so it's not bromine, it's bromide, right? Bromide. The next one, we have calcium. Calcium, I don't know if blue is the best choice for this one. Instead of iodine, we have iodide, okay? So calcium iodide. Next one, we have cesium. So cesium, like this. And then we have fluoride, Flu, fluoride, all right? Then we have lithium chloride. Then we have ammonium chloride. So remember, you've got to memorize that polyatomic ion, right? NH4 plus is ammonium, okay? So ammonium chloride. And the last one is, you could give it two possible names. You could call it sodium bicarbonate or sodium hydrogen carbonate. I'll just call it sodium bicarbonate. Sodium bicarbonate. Like that. Okay? So now what I think you could do is you could pause the video for a couple of seconds and then come back, and we'll name these last few compounds together. Okay, so let's see what you got here. The first one, I would call this sodium oxide. The next one would be cadmium sulfide. Next, we have magnesium nitride, so magnesium nitride, not nitrite. Next one, we have calcium phosphide, so calcium phosphide. Next, we have aluminum carbide, so carbide, okay? So aluminum carbide. Then we have aluminum carbonate. Again, you got to recognize that polyatomic ion. Aluminum carbonate. And the last one is going to be calcium sulfate. So calcium sulfate. Like that. So there you go. Now you know how to name an ionic compound. Now, what if you have a cation that could have more than one charge? And we see this with the transition metals, okay? Transition metals like tin and copper and iron and mercury, okay, they can have more than one charge. And so we have to specify what the charge is by using a Roman numeral. Now, if you take a look at the first two examples here, we have FeCl2 and FeCl3. So if we just unpack the FeCl2, well, what is the charge of Cl all the time when it's in an ionic compound, right? We know this is ionic because it's comprised of a metal and a nonmetal. Well, the answer is Cl is always -1, and there's two of them. So -1 times 2 gives me -2. So that tells me that the iron must be +2, okay? Whereas when we have FeCl3, right, we know that chlorine is always -1, but there's 3 of those, so that gives you -3. So that tells us the iron is +3. So how do I distinguish between the iron +2 and the iron +3? Again, we use Roman numerals. And so for the first one, we're going to call it iron, oops, let me get my pencil here. We're going to call it iron 2 chloride. And the second one, we're going to call it iron 3. So you got to maybe brush up on your Roman numerals, iron 3 chloride, like that. The next one, we have Hg2O, and then we have HgO. Okay, so we have Hg2O, and then we have HgO, like this. Well, the second one's actually a little bit less complex because oxygen is always 2-, so that tells us this is mercury 2. And this one, the first one, oxygen is 2-, sure. So that tells us that overall the mercury must be +2, but there's 2 of them, so each one is going to be +1. So Hg2O is going to be mercury 1 oxide, and HgO is going to be mercury 2 oxide. So mercury 2 oxide. All right, the next ones, I'll go a little faster here. The first one, so fluorine is always -1, so the first one must be tin 2 fluoride. Remember, it's Flu, so fluoride, and the next one must be tin 4 fluoride. All right, hopefully you can see those, and maybe I'll switch it like that. So tin 2 fluoride and tin 4 fluoride. And so now you've learned how to name ionic compounds that are comprised of a nonmetal and a transition metal that can have a variable charge. Now remember, there was 3 exceptions of transition metals that don't have variable charges, okay, just to review, okay, and we went over these quickly. There was 3 of them that kind of have this arrangement here, okay? So don't forget that they are zinc, okay, and cadmium, okay, and then we have silver over here. Silver is always +1, and these two guys are always +2. So just remember that moving forward. Now, before we can get into covalent nomenclature, we have to cover prefixes because prefixes are used when we name covalent compounds. And so if you have something like a polyatomic ion show up more than once, you would put di in front of it, right? Or sorry, if it shows up twice, rather, you'd put di in front of it. If it shows up 3 times, you put tri, tetra, penta, hexa, hepta, octa, nona, deca. You have to memorize these prefixes, okay? So these prefixes, we haven't used them yet because they're not part of the nomenclature of ionic compounds. The only time we use these prefixes, okay, we use Greek prefixes when we are naming what we call hydrate, and I'll cover that with you, and molecular compounds. That's when we use prefixes. So they're very, very important. Now, before we get into naming binary molecular compounds, I want to cover with you how to name a hydrate. So, if you're wondering, what the heck is a hydrate? Well, it turns out that when you have an ionic compound that contains, so ionic compounds have a crystal lattice, okay? And we've talked about a crystal lattice briefly in another lecture, okay? So we have a crystal lattice, that maybe looks something like this, okay? Where you have your cations and anions, but then you end up with these pockets inside, okay? These, pockets may be inside the crystal. And what happens is that water can fit inside the crystal, and when water gets trapped inside an ionic crystal, we call that a hydrate, okay? So when you have water inside the crystal. But the water is always going to be present in a fixed stoichiometric proportion, meaning like for every one of the ionic compound unit, you're going to have, an integer like 1 water molecule, 2 water molecules, 3, 4, 5, so on and so forth. And so you can, if you're wondering, can you remove the water from a hydrate? The answer is yes. If you heat it up, it will remove it, okay? And then you get an anhydrous compound. So the way that we name a hydrate is, first thing we're going to do is we're going to name the anhydrous compound, just like we always do. Then we're going to add the word hydrate as a suffix, or I guess after the initial name, okay? And then we use a Greek prefix, mono, di, tri, etc. to denote how many water molecules there are, okay? And so this is maybe, for some of you, your introduction to a stoichiometric coefficient, okay? Like this 5 that you see here. And what that means is, if we take a look at this first compound, right? If I just asked you to name CuSO4, you'd say, well, sulfate is 2 minus, so that means my copper is 2 plus. So if I just gave you CuSO4, you would call that copper 2 sulfate. But you see this little dot that's kind of hovering in midair, okay? That is what we put before the water molecules. And you see that for every one of these, right, because there's only one shown here, 1 copper 2 sulfate, we can put 5 water molecules in, okay? So we call that copper 2 sulfate pentahydrate. For the other one, right, you guys recognize calcium chloride. Well, in this case, the prefix isn't, or the coefficient isn't shown, so it's implied that it's a 1. So this would be mono, okay? So you'd call that calcium chloride monohydrate. All right? So anyhow, if we want to name a binary molecular compound, it says covalent bonding allows for significant variations in the ratios of atoms in a molecule. The names for molecular compounds must explicitly identify these ratios, right? A very simple example would be something like CO versus CO2. Right, you guys know that CO is carbon monoxide, right? So that tells you something. And CO2 is carbon dioxide, right? So if we need a name, we need a way to distinguish between them. So we use the prefix mono to denote that there's only 1 oxygen, and di to denote that there's 2 oxygens in this compound. So the name of the more metallic element, the one furthest to the left, is usually named first, like carbon. Okay, carbon is more metallic than oxygen, right, because it's further to the left in the periodic table. And then it says here, followed by the name of the more non-metallic element, oxygen in this case, and it's going to be further to the right. And you change the suffix to "ide." So instead of oxygen, it becomes oxide, right? If it was sulfur, it would be sulfide, so on and so forth. So the number of atoms of each element are designated by the nomenclature prefixes with a few exceptions, right? Students maybe don't love exceptions all that much, but you have to know a few of them, okay? And it says that when only 1 atom of the first element is present, you just leave the prefix mono out of it. And both of these examples illustrate that. We don't call this monocarbon monoxide. We don't call this monocarbon dioxide. So if the first element only shows up once, just eliminate the mono. The next one is if you have a binary compound, meaning an element made out of a molecule made out of 2 elements, and if it contains hydrogen, okay, it's going to have no prefixes. So if you have HCl, you just call it hydrogen chloride, right? If you have H2O, it's just called hydrogen oxide, right? You throw prefixes out completely. And I know every once in a while somebody will say, well, I have a sticker and it says dihydrogen monoxide or something. Well, that's incorrect. The correct name for water would just be hydrogen oxide. And then if you have 2 vowels that are adjacent, then the A in the Greek prefix is usually abandoned. And so if you have, let's see, let me think of something, dioxide, monoxide. Okay, so let's say you had something like N2O4. So if we had N2O4, you'd call this dinitrogen, but you wouldn't call it tetraoxide, okay? It says here the A is usually dropped. So instead of calling that, you would call it dinitrogen tetroxide, like that. Now, if you're wondering, is the whole first exam going to be just about that? Well, no, that's kind of splitting hairs. I usually don't pick on my students too hard about that, but it is a rule you're expected to pick up on, and you'll see the more you practice it, the more you will become accustomed to it. So let's see if we can name some binary molecular compounds, and this shouldn't take too long. The first one, we already named it. This is carbon monoxide. Remember, the first atom only shows up once, so we don't say monocarbon, right? The next one is carbon dioxide. Okay, I think we got those ones down. Then we have sulfur dioxide. Then we have boron. Remember, not monoboron, just boron because there's three of them. Not chlorine, chloride. Okay, moving right along, you have sulfur trioxide, so sulfur trioxide. We have, what's this one? I can't even see. I took my contacts out and just have my glasses. So sulfur hexafluoride, so this would be sulfur, right? Because there's only one sulfur. I can spell sulfur. Sulfur, and then there's 6 of them, so the prefix for 6 is hexafluoride. Okay, every once in a while I have somebody who will spell it like this. That's wrong, that's fluoride. I don't know what that is. The next one is nitrogen dioxide, so nitrogen dioxide. Then you have phosphorus pentafluoride, so phosphorus. I'm going to run out of space here. Pentafluoride. Okay, so what I recommend doing here is pausing the video, and then I'm gonna name these. So see if you can name them relatively quickly. Okay, let's see if we can name these. We've got dinitrogen tetroxide, so dinitrogen. It's not tetraoxide, it's tetroxide. Like that. Then we have dinitrogen pentoxide. Not pentaoxide, right? Pentoxide. Then we just have, remember, if there's hydrogen, we just get rid of all the prefixes. So hydrogen oxide. Right? Same thing for this one would be hydrogen sulfide. Right? Just ditch all the prefixes. Here you have tetraphosphorus decoxide, not decaoxide, just decoxide. So tetraphosphorus. I'm going to run out of space here. Phosphorus. Decoxide. Okay. And the last one we have, hey, what do you know? Tetraphosphorus decoxide. Okay, I guess there's a repeat in there. All right. Okay, so now if we want to name some acids, it says some compounds containing hydrogen are members of an important class of compounds known as acids. And one of the ways you can memorize acids, even though we're not going to look at this in detail yet, is they like to give up H plus ions, right? You see that right here. It says many acids release hydrogen ions when they're dissolved in water. But when you have an H plus ion dissolved in water, we call this a proton, okay? And if you think about it, if a hydrogen atom has 1 proton and 1 electron, and then you strip the electron away to make a cation, well, H plus is nothing more than a proton, all right? And it says a mixture of an acid with water is given a special name to denote this property. And to give you an example of what it's getting at here is, let's say you have HCl, right? No prefixes. HCl is actually a gas, okay? And it's called hydrogen chloride, right? Chloride. Not a big surprise there. But if you put HCl AQ, meaning, what does this mean? This AQ means it's a mixture of the acid with water. Then it's not hydrogen chloride. Then it's hydrochloric acid, okay? So you've got to be very careful with your phases of matter, whether it's a solid, liquid, or gas, or aqueous. And so to name a binary acid, it says use the name of the binary molecular compound as a starting point. Then the word hydrogen is changed to hydro. Okay, fine. Other non-metallic element name is modified by changing "ide" with "ic." Okay, and the words from 1 and 2 are combined into a single word. So hydrofluoric, right? Hydrochloric, right? Hydroiodic, etc. And then you just throw the word acid at the end. And so this first compound here, right, if it's a gas, this would be called hydrogen, right? All prefixes out the windows. Hydrogen fluoride, okay? But when it's HFAQ, you'd call this hydrofluoric acid. All right? Follow the same trend for the next one. This would be hydrogen chloride, right? And this would be hydrochloric acid. The next one, we have hydrogen bromide, and this would be hydrobromic acid. All right, next one would be hydrogen iodide, so hydrogen iodide, and so this would be hydroiodic acid. And the last one, this would be hydrogen sulfide, and so this would be hydrosulfuric acid. It's not sulfuric acid. Sulfuric acid would be H2SO4, okay? And so this is not sulfuric acid, this is hydrosulfuric acid. All right, now what if we have an oxygen in there, in our acid, okay? In that case, it says here to name an oxyacid, we get rid of hydrogen, so we leave that out. It says start with the root name of the anion, so I'll show you how to do that. Then you replace it, if your polyatomic ion ends with ate, like nitrate, you change it to ic. So from nitrate to nitric. And if it ends with ite, like nitrite, you change it to nitrous, okay? So if we have HNO3, the anion name NO3 is nitrate, okay? So that means we're going to change it to nitric. So HNO3 is nitric acid, like that. If you have NO2, that's the nitrite ion, so this would be nitrous acid, okay? Next one, if we have, this is the perchlorate ion, so we'll put here perchlorate, so that means it's going to be perchloric, right? So it would be perchloric acid. Next one is we have the carbonate ion here, so this would be carbonate, so carbonate. And so we would call this carbonic acid. And the last one, we have the sulfate, and so this would be sulfate, and so we would call this sulfuric acid. And there you go, that covers nomenclature. All right, so this is the content that we would have covered if we were going to have, or if we had class in person this evening.